Hi everybody. So in this video, we're going to look at calculating the probability of a type 1 and a type 2 error for a binomial, a Poisson, and a geometric distribution. And if you want to work along with me, you can download a copy of this PDF from my website. I'll leave a link below. So a probability of a type 1 error is when we reject the null hypothesis given that this is true. And I'll show you how to work this out as we work through example 1. So we're told that x is binomially distributed with a sample of 20, and the null hypothesis is that p equals 0.3, and we're testing this against the alternative where p is less than 0.3 using a 5% level of significance. The first thing we need to do is to work out the critical region. So if we assume that x is distributed with of 20 trials and a probability of 0.3, I'm just going to sketch this distribution. The peak of a distribution will be at the expected value of x, which is n times p. So this will be at 6. Because the alternative hypothesis is p is less than 0.3, our tail will be to the left of the expected value. So I've shown that here. To work out the critical region, we need to work out this value, which I'll call c. So we're looking at the probability of our random variable being less than or equal to the observed value c, which must be less than the significance level of 0.05. We can work out this critical value from our tables. So we have our probability of 0.3 with 20 trials, and we're looking at the first cumulative probability that goes above the 5%, which is when x equals 3. So our critical value will be when x is less than or equal to 2, which is here. And this will have a cumulative probability of 0.0355. So if we go back to our notebook, the probability of x being less than or equal to 2 will be equal to 0.0355. So I'll label this critical value on the diagram. This is with 2. So our critical region, where we reject HO, is when x is less than or equal to 2. Okay? And then for part B, find the probability of a type 1 error. Well, the type 1 error, we must reject HO given that HO is true. So this model is true and we reject, which means we must be in this critical region. So it's asking what is the probability of being in this critical region? And we've just found this as 0.0355. So for part B, the probability of a type 1 error will be 0.0355. That's the probability of being in this region given that this model is true. And then for part C, given that the true value of p was later found to be 0.25, find the probability of a type 2 error. So a type 2 error is when we accept HO. So we must be to the right of this critical value, given that HO is false. So our model is false, but we are to the right of the critical value. So the way we write this is the probability of a type 2 error will be falling to the right of this critical region. So we're looking at the probability of x being greater than or equal to 3, given that p is actually 0.25. And we can work out this probability as 1 minus the probability that x is less than or equal to 2. And we can work this out on our calculators. So if we go to home and distribution, we want binomial CD, variable, we'll choose x is 2, n is 20, and p is 0.25. We'll execute that, So we get 1 minus 0.0913. If we go home and calculate 1 minus the answer, we get the probability of a type 2 error to be 0.9087. Okay, let's look at a Poisson distribution. So now we're given a random variable y as a Poisson distribution, and a sample is taken to test the null hypothesis that lambda equals 8 against the alternative hypothesis that lambda does not equal 8. So this will be a two-tailed test using a 10% level of significance. So if we assume that y is distributed with a Poisson lambda 8, and we sketch this model, it will look something like this, where the expected value is at the average. Then because of this alternative hypothesis, the critical region could be less than, we'll call it C1, and greater than. And each of these areas will have a probability of half of the level of significance. So this will be at 0.05, and this will be at 0.05. So we need the probability of y, if we're looking at C1, to be less than or equal to C1, to be less than the 5%, and the probability of y being greater than or equal to C2 to be, again, less than the 5%. So we can work this out from our tables. We've got lambda equals 8, and we want the first probability to go above the 5%, which is the 0.0996. So this will be our critical value when y is less than or equal to 3. And it will give us a probability of 0.0424. So we'll say the probability of y being less than or equal to 3 is 0.0424. And now we need to work out C2. And we can work out C2 if we go to our tables. So now we're looking at the probabilities nearest to 95%, which are when x is less than or equal to 12 and when x is less than or equal to 13. So we need to make a note of these two probabilities, okay? If we go back to our notebook, the probability of y being less than or equal to 12 was 0.9362. So the probability of y being greater than or equal to 13 will be 1 minus this, which gives us 0.0638. And then the other one was when we had y is less than or equal to 13, which gave us 0.9658. So probability of y being greater than or equal to 14 will be 1 minus that. And this will give us 0.0342. And you can see that this probability is closer to the 5%. So our critical regions will be when y is less than or equal to 3 or when y is greater than or equal to 13. And then for part B, find the probability of a type 1 error. Well, this means we reject HO given that HO is true. So it's the probability of us being in either of these critical regions. So the probability of a type 1 error will be the probability of y being less than or equal to 3, which is this one, or the probability of y being greater than or equal to 13, which is this one. So we'll add these two together. And we get 0.1062. So this is the probability of a type 1 error. Then for part C, given that the true value of lambda was later found to be 7, find the probability of a type 2 error. Well, this is when we accept HO So we must be outside of the critical regions, but given that HO is false, so this model is false, and we're told that lambda is actually equal to 7. So the probability of a type 2 error is when y is less than the 13, so less than or equal to 12, but greater than the 3, so less than or equal to 4, given that lambda actually equals 7. We can work this out as the probability of y being less than or equal to 12 minus the probability of y being less than or equal to 3. If we go back to our calculators, we'll choose distribution. We want Poisson cumulative. We'll choose variable. We want our y value to be 12, lambda to be 7. We'll execute that, and we get 0.973. We'll go back, and now we want y to be 3, and we get 0.0817. So if we go home, we want 0.973 minus 0.0817. And this will give us our probability of a type 2 error as 0.8913. Okay? Let's try one more question on a geometric distribution. So now we're told that the random variable w is geometrically distributed, and a sample is taken to test the null hypothesis that p equals 0.2 against the alternative that p is less than 0.2 using a 5% level of significance. We need to calculate the critical region for the test. So perhaps you want to try this question yourself. You can pause the video, and when you come back, we'll go through the solution. Okay, so welcome back if you had a go. So if we assume then that W is distributed geometrically with a probability of 0.2, I'm going to sketch his geometric distribution. We know the expected value will be a 1 over p, so 5. So because p is less than 0.2, and this is a geometric distribution, our tail will be to the right of the expected value. So I'll label this as C, and this region will have a probability of 0.05. This will be the area. So we require the probability of W being greater than or equal to C to be less than 0.05. And we know the equation for this we covered in hypothesis testing. This will be 1 minus P. So 1 minus 0.2 will be 0.8 to the power of C minus 1 will be less than 0.05. If you're not sure how I covered this, you should check out my video on hypothesis testing with geometric distribution. Now we can use logs to bring this power down. So we get C minus 1 multiplied by the log. Our natural log of 0.8 will be less than the natural log of 0.05. When we divide both sides by this, we need to change the sign because this is negative. So C minus 1 will be greater than the log of 0.05 over the natural log of 0.8. We'll add 1 to both sides. So C must be greater than 14.425. But we know that this is a discrete value, so C must be greater than or equal to 15. So our critical region is when W is greater than or equal to 15. I'll label this on the diagram here. Okay? Then for part B, so the probability of a type 1 error is when we reject HO, so we must be in this critical region, given that HO is true, so given this model is true. So this will be the probability of W being greater than or equal to 15 given that P equals 0.2, which will be 1 minus the 0.2 to the 15 take away 1, so 0.8 to the power of 14, which gives us 0.044, okay? And then for part C, given that the true value of P was later found to be 0.35, find the probability of a type 2 error. So a probability of a type 2 error, we must accept HO, given that HO is false. So we'll be on this side of the critical region. So we want the probability of W being less than or equal to 14, given that P is actually the 0.35. And because W is less than or equal to 14, we calculate this as 1 minus 0.35 to the power of that 14. So we want 1 minus the 0.65 to the 14, which gives us 0.9976 to 4 dp. Okay? Well, thank you very much for watching. I hope you found that useful. If you did find that helpful, please like and subscribe, and you can download the full lesson and a PDF that accompanies this video from my website, mrmathematics.com. I'll leave a link below.